Section 1. Origins of light absorption. From the cosmos to the cuvette.
Okay, believe it or not, this whole thing didn't actually start in a pristine chemistry lab at all. It started with an astronomer named Pierre Bouguer. He was out there observing starlight, trying to calculate the height of the Earth's atmosphere, and he realized something profound. Light drops off geometrically, or exponentially, as it travels through an absorbing medium. This totally laid the groundwork for Johann Heinrich Lambert and later August Beer, who proved that the concentration of a solute in a liquid has the exact same exponential effect on light as the thickness of the atmosphere.
Moving on to Section 2, Decoding the Law, the math behind the gauntlet. This brings us to the famous formula at the heart of it all. A equals epsilon Cl. Think of it like this. Your photon is running a gauntlet of absorbing molecules. The more molecules there are, that's your concentration, C, or the longer the path length it has to travel, that's L, the fewer photons actually survive to hit the detector. And what exactly is eating those photons? It's the electronic and vibrational transitions within the molecules themselves, absorbing very specific energies. If you think about a UV-Vis absorption spectrum, those distinct, beautiful peaks you see match perfectly with these specific transitions absorbing distinct wavelengths of light. The higher the peak, the more light is getting absorbed right there. And that proportionality constant, epsilon, that just tells us exactly how strong of an absorber that specific molecule actually is.
Which brings us to Section 3, Transmittance to Absorbance.
The digital transformation.
So the really crucial point here is how we mathematically flip those surviving transmitted photons into a super useful linear measurement that we call absorbance. Because remember, transmittance, the light that actually makes it through, drops off exponentially. To see that exponential drop-off quantified, just look at these numbers. An absorbance of 3 doesn't just mean your solution is, kind of dark. It means 99.9% of the incident photons have been totally eaten by the sample. Literally only 0.1% of the light made it out. This is exactly why analytical chemists are always chasing that sweet spot between 0.2 and 0.5 absorbance. It keeps your signal linear and reliable.
And to give you a real sense of scale regarding how powerfully some molecules can absorb light, look at this number. 10 to the 5th power. I mean, typical DD transitions in transition metals are pretty modest, giving you low epsilon values. But the absorptivity of highly colored species with charge transfer bands, they can hit a massive 100,000 liters per mole per centimeter.
Time for a little vocabulary update. Memorize this term. When you see epsilon in the Beer-Lambert equation, this is exactly what it stands for, assuming you're dealing with pure unscattered absorption. Section 5. Lab realities and law deviations. Let's look at when the rules actually break down.
Because, look, theory is amazing. But in the harsh reality of the lab, the Beer-Lambert law isn't some universal constant. It's an idealized approximation. To stop catastrophic scattering errors from wrecking your data, you have to follow strict steps to prep your cuvette gauntlet. You need a perfectly homogeneous medium. Honestly, if there's an undissolved particle or a microscopic bubble or even just a fingerprint on the glass, your instrument is going to read that scattered light as absorbance. It creates a totally artificial deviation. So sonicate your samples if you have to.
Getting back to law deviations, this specific number right here, 0.01 molar, is actually a critical concentration threshold. Once your sample hits a concentration higher than this, the molecules are quite literally packed so tight that their electrostatic interactions start altering each other's charge distributions. That fundamentally shifts the energy needed for those electronic transitions, which basically causes the Beer-Lambert law to break down, giving you a really frustrating nonlinear calibration plot.
Plus, your measurements will start to drift if you violate any of these strict physical parameters. I really want to highlight a huge one, spectral bandwidth. Your incident light needs to be incredibly monochromatic. If the bandwidth of the light hitting your sample is wider than the natural line width of the absorption peak you are trying to measure, you are going to absolutely crush your peak resolution, and your calibration curve is going to curve right downwards. Finally, Section 6, Advanced Quantitative Techniques. solving for complex deviations.
So, what do you do when your chemical equilibria shift out of nowhere, or high concentrations totally ruined your linear calibration curve? Well, there's a really clever workaround called absorbance matching. Instead of relying on a broad, potentially flawed linear range, you just systematically dilute your unknown sample until its absorbance perfectly matches a single, known reference standard. It is a beautifully precise comparative trick that basically neutralizes instrument nonlinearities altogether.
Another incredibly powerful tool is multi-wavelength analysis. By measuring at multiple wavelengths, we can mathematically subtract out messy background scattering and analyze really complex mixtures. I want to leave you with a bit of a provocative thought. We are currently building these brilliant, structured digital databases for the future. But as AI models start ingesting centuries of our messy, completely unstandardized scientific past, data filled with old terms like optical densities and extinction coefficients, how will they decipher the truth? It's a fascinating collision between modern structured data and our very human history. And it's something every modern scientist is going to have to navigate. Anyway, thank you so much for joining me on this explainer. Keep your cuvette spotless and never stop questioning your data.